Good morning, everyone. It's a real pleasure to be here. My name is Aletha De Witt, and today I'll take you on a journey through the world of VLBI. That's Very Long Baseline Interferometry, and how this technique connects astrometry and geodesy to help define both where we are on Earth and where things are in the sky. Okay, so here's our roadmap for the talk. We'll start by asking, what is VLBI? Then we'll take a brief historical journey to understand where it came from. We'll look at why we observe in the radio, what VLBI measures, and the kinds of applications that it supports. Then we'll dig into how VLBI works, from telescopes and networks to the celestial objects we observe. Finally, we'll look at how VLBI contributes to global geodesy and close with a look at next-generation systems. So, let's start at the beginning. What exactly is VLBI? We've laid out the roadmap and now we're stepping into the heart of it. Very long baseline interferometry. Might sound like a mouthful, but essentially VLBI is the technique that lets us determine ultra-precise positions on Earth and in space by comparing the time delay of radio signals from the most distant celestial objects received at different radio telescopes spread around the world. This time delay holds a wealth of information about Earth's orientation and motion. What we are doing with VLBI today, observing celestial objects to determine time and position, is really part of an ancient tradition that goes back at least 5,000 years. Some of the earliest observatories, like those on Malta, as shown in the slide, were aligned to the stars and seasons. So while we're using cutting-edge radio telescopes and atomic clocks, we're really continuing an ancient human effort, tracking the heavens to understand our place on Earth. To understand why VLBI is such a powerful tool in geodesy and astrometry, it helps to see how far positional measurements have come. We already know that for thousands of years, humans tracked the stars, but precise astrometry began with Hipparchus in 130 BC, who noticed the precession of the equinoxes using only the naked eye. Quite impressive. Fast forward to the telescopic era, and we begin to see major breakthroughs. In 1718, Halley discovered proper motions of stars, and by 1838, Bessel measured stellar parallax, confirming that stars were at vastly different distances. By the 20th century, optical astronomy was hitting a wall. The atmosphere blurred our view, and stars shifted due to their own motions. Then came a revolution. In the 1930s, radio astronomy was born. By the 1960s, radar technology, atomic clocks, and massive antennas came together to create VLBI, Very Long Baseline Interferometry. It allowed radio telescopes thousands of kilometers apart to act as a single instrument, recording and precisely time-tagging signals from the most distant extragalactic radio sources. VLBI unlocked a new era. It gave us access to stable sources, the quasars, almost perfect fixed points in the sky, and it enabled the construction of the International Celestial Reference Frame, a more stable celestial frame, replacing the moving star-based optical frames. At the same time, it became a cornerstone of geodesy, measuring tectonic motion, tracking Earth's rotation, determining station positions with millimeter accuracy, and contributing to the ITRF. So you may wonder, why use radio waves? Well, for one, they let us observe day or night and even through clouds. But single radio telescopes have limited spatial resolution, so the real magic happens when we combine telescopes thousands of kilometers apart, effectively creating a virtual telescope the size of the Earth. The distance between them is called a baseline. This setup gives us insane resolution, around 50 times better than the Hubble Space Telescope. So the second reason we observe in the radio part of the spectrum is the radio window. The Earth's atmosphere blocks most wavelengths, except for this beautiful radio window. We can observe radio waves from space without needing to launch anything into orbit. That makes it practical and powerful. So, coming from resolution and access to the radio sky, the question now becomes, what do we actually do with VLBI? Well, the answer is a lot. For one, it gives us the celestial reference frame, which in turn provides calibrators for astronomy and also enables differential astrometry of the positions, parallax, and proper motions of objects in our galaxy, like mapping the structure of the Milky Way's arms. It's also essential for planetary ephemeris alignment, for navigating interplanetary spacecraft, for satellite tracking and precise orbit determination, and even for testing Einstein's theories. And of course, it contributes directly to geodesy and the Global Geodetic Reference Frame. So VLBI isn't just cool for science, it's truly like the Swiss Army knife of Earth space positioning. Now that we've seen what VLBI can do, let's look at where it fits in the bigger picture. This schematic shows how VLBI links everything together. At the heart of it, VLBI measures the Earth's orientation in space, how the Earth spins, wobbles, and shifts. These Earth orientation parameters act as the bridge between two key reference frames: the celestial reference frame, a fixed backdrop of distant quasars defined by VLBI, and the terrestrial reference frame, a dynamic model of Earth's surface to which GPS, satellite orbits, and ground stations are tied. VLBI ties these two together. It's what makes global navigation, satellite tracking, and precision positioning possible across Earth and space. So in many ways, this technique is the glue holding together our understanding of where we are and how we move, both on Earth and in space. Now let's zoom out for a second. How does VLBI actually help us understand the Earth system? To measure things like plate motion or sea level change, we need stable reference frames, one fixed to the Earth and one fixed to the sky. VLBI does this by observing the quasars, incredibly distant galaxies with bright active cores, and they are so far away that they don't appear to move at all, making them perfect anchors for our celestial reference frame. On the ground, we place radio telescopes at fundamental geodetic sites on the Earth's crust. These telescopes observe quasars simultaneously, and by comparing the time that signals arrive, we measure incredibly small differences. This allows us to track how the Earth rotates, like UT1 and polar motion, how it moves, tectonic drift and station positions, and how we tie the sky and the Earth together. In short, VLBI connects us to the cosmos, and it anchors our measurements here on Earth. Without it, we'd be adrift, scientifically and literally. So here's where VLBI really stands out among the geodetic techniques. First and most importantly, VLBI uniquely defines the International Celestial Reference Frame. It's the only technique that observes distant quasars directly, giving us fixed points in the sky to anchor all space-based measurements. Secondly, it directly measures Earth's rotation, specifically UT1 minus UTC, something no other technique can do on its own. That's absolutely critical for aligning satellite observations with the Earth's true orientation in space. Beyond that, VLBI contributes in 5 key ways. It provides precise 3D positions and velocities of fundamental stations for the ITRF, and it helps define the absolute scale of the reference frame. It uniquely determines UT1 minus UTC, as I've already said, but it also contributes to polar motion and nutation. And it also offers long-term stability with decades of continuous observations from globally distributed sites. And crucially, it's the only technique that directly connects the terrestrial and the celestial reference frames, ensuring Earth-based coordinates are properly oriented in inertial space. So in summary, VLBI may be just one technique, but it's the one that ties everything together. So here are some real-world examples of what VLBI can measure. The top left shows the ICRF, our latest international celestial reference frame built using VLBI. And in the top right, we show tectonic motion measured by VLBI. The bottom left shows how VLBI helps us monitor changes in Earth's rotation. It shows that the length of day is increasing very slowly over time as Earth's spin gradually slows down. And bottom right is VLBI measuring the baseline between South Africa and Japan, showing nearly half a meter jump after the 2011 earthquake in Japan. Now let's walk through how VLBI actually works. It's conceptually simple but incredibly powerful. Imagine a distant radio source, usually a quasar, sending out waves that reach Earth. Now one wavefront hits a telescope, say for example in South Africa, and a split second later that same wavefront hits a second telescope, for example in Japan. Now that time difference between hitting the first and then the second antenna is called the geometric delay, and this holds the key to positioning. At each station, the incoming signal is converted into a time-sampled voltage stream and recorded with ultra-precise time tags, thanks to hydrogen maser atomic clocks. These time tags tell us exactly when the signal was received. Then later, at what we call a correlator, we slide the signals from the different telescopes back and forth to find the best match. That match tells us the time delay between when the wavefront hit each telescope, and that is our core observable. Now, of course, longer baselines or longer distances between two telescopes mean we're more sensitive to the source's position on the sky, and that's why long baselines are absolutely essential for astrometry and geodesy. Okay, so the core observable in VLBI is the time delay. That's what we measure, and by precisely modeling these delays across the global network, we can solve for three things: the positions of the radio telescopes on Earth, the positions of the quasars in the sky, and the Earth's orientation in space at the time of each observation. So every pair of telescopes forms a baseline, and each delay measurement gives us a geometric constraint, essentially telling us how that baseline sees the sky. To tie it all together, we use rotation matrices to convert from the terrestrial reference frame, where the telescopes sit, to the celestial frame, where the quasars live. That transformation depends on the Earth orientation parameters. Now, this is what makes VLBI so powerful. In a single 24-hour session, a global network of radio telescopes observes dozens of quasars, and all those delay measurements from all baselines and scans are combined into one global solution, giving us positions, orientation, and time with incredible precision. Okay, so let's break down what's actually inside this delay that VLBI measures. The dominant part is the geometric delay. It's just the extra distance the wavefront travels to reach one telescope before the other, divided by the speed of light. But that's not all. There are other important contributors we need to model or correct for. For example, the atmospheric delay, especially from the troposphere and ionosphere, instrumental delays from cables, electronics, and clocks, things like relativistic effects, and then there's of course also source structure, which we usually don't model, but it can affect the delay if the quasar isn't a perfect point source. So all of these components gets wrapped up into our delay model, and by fitting everything together carefully, we can extract incredibly precise information about the Earth, the telescopes, and the universe beyond. So this is what a VLBI radio telescope looks like in action. In short, a parabolic dish collects incoming radio waves and focuses them onto a feed horn, where the signal is then converted into an electric current. Signals are sent to a control room, time-tagged with an atomic clock, and recorded. And later, all the signals from different telescopes are combined at a correlator to extract the delays that we need. In essence, this is a mix of precision engineering and clever physics, with every part of the setup working together to detect and timestamp signals from distant radio sources with extreme accuracy. So here we see the global distribution of VLBI telescopes that contributed to the ITRF 2020, and they're shown here as yellow stars on the map. And what stand out is how few of them are in the southern hemisphere, and this is a clear gap that we are still working to close. And now looking at the VLBI stations that contributed to the ICRF3, we see that the pattern is similar. And again, there's a noticeable imbalance, far more coverage in the northern hemisphere, which limits our ability to model the sky uniformly. Now, the core idea behind geodetic and astrometric VLBI is simple. We want to use point sources at infinity to define directions in space. And the most stable and distant reference points that we can find are quasars. Quasars, which were discovered in 1962, are the bright, energetic cores of extragalactic galaxies, and these are powered by supermassive black holes that's feeding on gas and dust. Now, these quasars, being billions of light years away, are about as close as we can get to a true point source at infinity. They don't move, and that's exactly what we need. But there's a catch. Because they're so far away, the signals we receive from quasars are incredibly faint. So how do we actually observe them? Well, we need big radio telescopes, typically at least 20 meters in diameter. We also need a lot of bandwidth to capture as much signal as possible. And finally, we need to cryogenically cool our receivers to get the system temperatures down, just to make sure we're not drowning the signal in noise. So yes, quasars are almost perfect, but they don't make life easy. So what I'm showing here are VLBI images of real quasar sources that we observed at 24 gigahertz. And now it's important to note that while we treat quasars as point sources, in reality, some of them have some structure, jets or even multiple components. Now, the majority of these quasars that we observe are compact and clean, and they are ideal for reference frames, but there are others that's extended, double, or variable, which make them very hard to model. Now, understanding the structure is key for improving our VLBI accuracy, especially as we push towards micro-arcsecond precision. So how do we actually coordinate VLBI observations and turn them into precise geodetic products? Now, this is where the International VLBI Service for Geodesy and Astrometry comes in, or the IVS. Now, the IVS is the international body responsible for organizing all astrometric and geodetic VLBI observations, processing the data and delivering key products like the celestial and terrestrial reference frames and Earth orientation parameters. The IVS was founded in 1999 as a service of the International Association of Geodesy, and it was also recognized by the International Astronomical Union in 2000, and it's also a member of the World Data Center since 2011. So today the IVS includes around 88 permanent components involving 41 organizations across 21 countries and with more than 300 active members. Now, the IVS is made up of institutes and observatories that operate VLBI telescopes and networks, run correlators and data centers, and perform analysis, technology development, and coordination. Okay, so the IVS coordinates several types of VLBI sessions, each designed with a specific goal. So there are some 24-hour sessions that's focused on determining the Earth orientation parameters, and others targeted specifically at the terrestrial reference frame by refining station positions, and then some sessions is focused on improving the celestial reference frame. There's also what we call intensive sessions, which are these short 1-hour observations that's run daily, specifically for determining UT1 minus UTC with low latency. And then, of course, the new VGOS sessions, which is using a new broadband network. And these are rapidly expanding in coverage and frequency. And then, of course, the IVS doesn't just coordinate observations, it also delivers a wide range of geodetic products that support global reference frames and Earth orientation. For example, a time series of telescope positions and velocities and baseline lengths, time series of quasar positions, tropospheric parameters, and of course, the full set of Earth orientation parameters. So we're not quite done yet because the future of VLBI is already underway. And of course, to meet the challenges of the coming decades, which requires higher precision, faster data delivery, and continuous global coverage, we needed a VLBI system that's built for the next generation. And that's exactly what VGOS, or the VLBI Global Observing System, is. So we've now entered the VGOS era. And this basically is a modern upgrade for geodesy and astrometry. So it brings faster broadband antennas with much wider frequency coverage and much higher data rates to handle all of this. So the goal here is 1 millimeter positioning accuracy, sub 10 micro-arcsecond angular precision, and continuous 24/7 observations with rapid turnaround of results in less than a day. So right now, around 13 VGOS stations are operational worldwide, and that number is rapidly growing. So this is a major leap forward, and VGOS is aiming to improve accuracy by a full order of magnitude compared to the older or legacy SX systems that was used before. So alongside VGOS, there's also another major development, which is focused not so much on how we observe, but rather what we observe. And this effort is called K-band VLBI, and it involves observing at a much higher radio frequency, 24 gigahertz, and using many of the large legacy VLBI telescopes. So why K-band? And this is because it brings several key advantages like higher angular resolution observations, reduced plasma effects on core shifts, which distort source positions at lower frequencies, and also it gives us more compact and stable structure for the quasars that we observed. So K-band VLBI has already made enormous progress, both in terms of celestial reference framework and also supporting geodetic products. And K-band VLBI isn't just an experiment anymore. It's now a serious, coordinated effort that's pushing the limits of modern astrometry and geodesy. Okay, so that's it from my side. This is the end of the presentation. So thank you all, and I'm happy to take any questions or comments. Thanks.